Okay, let's look at what the graphs of all 6 of these trig functions look like. And when we graph them, our independent variable x is going to be the angle of rotation in radians, and our dependent variable y are going to be these 6 trig ratios. So before we start graphing these, make sure you've gone to the link in the description so you can get a copy of the blank lesson so you can follow along. And also, if you follow the link, you'll see lesson solutions and practice questions along with solutions. So let's get started. Before we start graphing the functions, we're going to have to remember a couple tools we can use to evaluate trig ratios. And these should be reviewed, so I'll go through them quickly. The first one being a unit circle, a circle that is centered at the origin and has a radius of 1 unit. That's why it's called a unit circle. I've drawn it here. Here's a unit circle, centered at the origin. Radius of this circle is 1. Now, if we know where terminal arm intersects the unit circle, so if we know the xy coordinate of the point where it intersects the unit circle, the x and y coordinates actually reveal to us the cosine and the sine ratios for the angle of rotation, which I've labeled here as theta. And the angle of rotation is always the angle between the initial arm, the positive x-axis, and the terminal arm. So if we know where the terminal arm, which can rotate counterclockwise around this unit circle, if we know where that terminal arm intersects the unit circle, we know the cosine and sine ratios. And if you remember SOHCAHTOA, that should be obvious to you, right? Sine of an angle is equal to opposite over hypotenuse, right? To get to this xy coordinate, I'd have to go x that way and y that way. That's why I've labeled the sides of this triangle those. And this is a right triangle, so we could use SOHCAHTOA, right? Sine of theta would equal y over 1. So I can fill that out here. Sine theta is y over 1. Y divided by 1 is just y. So that tells us the value of sine theta is equal to the y coordinate of where we intersect the unit circle. That's important. So sine theta equals the y coordinate where we intersect the unit circle. If we were to do from this angle of rotation, from this principal angle, cos theta equals adjacent x over hypotenuse 1. So x over 1, which is just x, that tells us the value of cos theta is equal to the x coordinate of where we intersect the unit circle. So when is this unit circle going to be most useful? Well, when do we know the x and y coordinates of where this terminal arm will intersect the unit circle? Well, I would know at these 4 blue points that I've labeled. Because this circle has a radius of 1, I know this is point 1, 0, and so on. This is 0, 1, negative 1, 0, and 0, negative 1. So these are the angles of rotation where I would know the x and y coordinates exactly. And remember, in radians, this is 0, right? This is the initial arm, positive x-axis. We start here, and then we rotate counterclockwise from there 90 degrees, which is pi over 2 radians. Another 90 degrees brings us to pi radians. Another 90 degrees brings us to 3 pi over 2 radians. Another 90 degrees brings us to 2 pi radians. So let's get a visual demonstration of what I'm talking about here. So let's start with the sine graph here. So I want you to be paying attention to the value of the sine ratio, which can be represented with this dot here. How that corresponds to the y coordinate of the dot on the unit circle. So notice that this yellow dot and this yellow dot are going to match up exactly. And on the x-axis here, we have angle of rotation in degrees, which is fine for our understanding of this. So as I rotate around the unit circle, notice that the y coordinate where we intersect the unit circle is equal to the value of the sine ratio, right? This is labeling the y coordinate of where we intersect the unit circle, and this is labeling the sine ratio. And notice that they stay equal. The highest they go is 1, back to 0. Lowest it goes is negative 1, back to 0. And then there's one cycle of sine. Let's now look at cosine. Cosine, the x coordinate where we intersect the unit circle. This pink line here is showing us the length of the x side, right? So it tells us the x coordinate is 0.5. And notice that that matches exactly to the cosine ratio, which is on the y-axis of our graph here. X-axis is still angle of rotation. And as I rotate around, the x coordinate of where I intersect the unit circle, so this, the x coordinate of this matches the cosine ratio. And as we rotate around, x coordinate goes to negative 1, x coordinate goes to 0, x coordinate goes to 1. And I'm talking about the x coordinate of where these intersect the unit circle and how that matches the cosine ratio plotted on this function here. So here we go. Let's graph sine. And we're going to graph it at pi over 6 interval. So at every 30-degree interval, we're going to come up with the sine ratio value. And we're going to do that, like I said, using the unit circle and the special triangles. Here's the special triangles, right? The isosceles 1, 1, root 2 triangle, where these two angles are both pi over 4, right? They're both 45 degrees. and the half equilateral special triangle, where we have 60 degree, which is pi over 3, and 30 degree, which is pi over 6 angles, and it's 2, 1, root 3 are our sides. So using these tools, we should be able to fill out all of these ratios. Let's go through quadrant 1 first. So we start here at an angle of rotation of 0 radians. So sine of 0, I know it intersects the unit circle right there. The y-coordinate is 0, so the sine ratio is 0. Sine of pi over 6, go up here, so SOHCAHTOA, opposite over hypotenuse, it's a half, which is 0.5. Sine of pi over 3, also in special triangle, opposite over hypotenuse is root 3 over 2, which is approximately 0.87. Sine of pi over 2 intersects the unit circle here, y-coordinate is 1. Now let's do the angles in quadrant 2, right? Here's quadrant 2. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. So I'm going to need to know the cast rule when I figure out the ratios in the following 3 quadrants. In this quadrant, sine is still going to be positive because the y-coordinates are all positive. In this quadrant and this quadrant, the sine ratios are going to be negative because y-coordinates below the x-axis are negative. So let's go through the ratios for quadrant 2, and we're going to have to use reference angles to find them. So 2 pi over 3, well, the principal angle, if I rotate 2 pi over 3 from here, it would be roughly about here, with a reference angle of pi minus 2 pi over 3, which is 1 pi over 3. So the reference angle is pi over 3. So I can use sine of pi over 3, which is root 3 over 2, and I can leave it positive because I know in this quadrant sine is positive, right? The y-coordinates are still positive. So the sine ratio of 2 pi over 3 is the same as pi over 3. 5 pi over 6, well, the reference angle is pi over 6, so I can just do sine of pi over 6, which is a half. And sine of pi, the y-coordinate of this point right here, is 0. How about quadrant 3? Well, in this quadrant, sine is negative, right? Only tan is positive here because y-coordinates here are negative. So if I wanted sine of 7 pi over 6, well, 7 pi over 6 would intersect the unit circle about there with a reference angle of pi over 6, right? Reference angle is always between terminal arm and x-axis. So I can do sine of pi over 6, if we look at our special triangle, is 1 over 2, but I have to make it negative because we are in the tan quadrant where sine is negative, right? The y-coordinate of that point would be negative, so the sine ratio is negative. So we can do sine of the related angle, which is pi over 6, but then make it negative. 4 pi over 3, the reference angle will be pi over 3, so I could do sine of pi over 3 is root 3 over 2, but I'm in quadrant number 3, so I know it has to be negative, root 3 over 2, so negative 0.87. And then sine of 3 pi over 2, the y-coordinate's negative 1. And then we're going back up, right? The y-coordinates are going to go back up. They're still going to be negative, so it's going to go from negative 1. And then now sine of 5 pi over 3, use the reference angle pi over 3, root 3 over 2, but keep it negative. And then sine of 11 pi over 6 is going to be equal to negative sine pi over 6, right? Because 11 pi over 6 is about here, reference angle pi over 6. So sine of pi over 6 is a half, so sine of 11 pi over 6 is negative a half. And sine of 2 pi, y-coordinate is 0. Now if I plot all of these points, I'll get one cycle of the sine function. So each of these is an xy point, right? Point 0, 0, point pi over 6, 0.5, and so on. So let's plot each of these points on our grid, where I already have the x-axis labeled for you going up at pi over 6 intervals, and the y-axis is going up by 0.25s. So here's what the first cycle of the sine function looks like. So there's one cycle of the sine function, and sine is a periodic function. This cycle just repeats over and over and over again. So I could do another cycle to the left over here. If I just imagine copy and pasting this cycle over here, we'll continue our pattern, we'll get another full cycle of this. And I'll do it in a different color just so you can see the distinction between the two cycles. So there's the second cycle of the sine function. And keep in mind, the x-axis is the angle of rotation, and the y-axis is the actual value of the sine ratio for that angle of rotation. So x sine x. Now let's graph the cosine function using the same tools, but when we use the unit circle, we're now looking at the x-coordinate where it intersects the unit circle. So the x-coordinate of 0 radians is 1. For pi over 2 radians is 0. For pi radians, it's negative 1. For 3 pi over 2, it's back to 0. And for 2 pi, we're back to where we started at an x-coordinate of 1. And then we'll fill in the ones in between using our special triangles and the cast rule. So quadrant 1 is the easiest. Cos of pi over 6 adjacent over hypotenuse is root 3 over 2, which is 0.87. Pi over 3 cosine is a half, which is 0.5. 2 pi over 3, we're now in this quadrant, which has a reference angle of pi over 3, so I can do cos of pi over 3, but notice the x-coordinate where we intersect is going to be negative, so I have to make it negative, right? That's what this tells us. Only sine is positive here, so cosine is negative. So cos of 2 pi over 3 is equal to the negative of cos pi over 3. So that'd be negative a half. Cos 5 pi over 6 would equal negative of cos pi over 6, so negative root 3 over 2. And cos of pi, we already did that, is negative 1. Now let's go through quadrant 3 and quadrant 4, once again using reference angles and the cast rule. So cos of 7 pi over 6, 7 pi over 6 is about here, reference angle of pi over 6. So I can do cos of pi over 6, root 3 over 2, but I have to make it negative because I'm in the tan quadrant. And I think you get the pattern now, so I'll just fill out the rest of these quickly for you. Now let's plot each of these points, and we'll get a good picture of what the cosine function looks like. So there's one cycle of the cosine function, and now let's do a second cycle of it. I'll do it in a different color again. So there's my second cycle of the cosine function. Okay, let's write down some properties of these two functions that we just graphed, sine and cosine. So we're going to talk about domain and range, and amplitude and period of these functions. So domain, what angle of x could we input into the function? Well, where along the x-axis does this function exist? It exists everywhere. There are no restrictions on the domain. X could be any real number. Range, however, if we look at this function, the y values are always between negative 1 is the lowest it goes, and the highest it goes is 1. So the range, y can be any real number that is within that interval. So we can write that like this. Y is any real number, given that y is between, including, negative 1 and 1. The period of sine and cosine is 2 pi. That's how long it takes to do one complete cycle. And amplitude of the function is the distance from the midline of the function. So the midline, picture the x-axis dividing this function horizontally in half. The distance between that line and the max, or that line and the min, we call that the amplitude of the function, and that distance is 1 unit. We could also calculate that by doing max minus min over 2 to calculate the amplitude. So let's do that. Max minus min over 2. So 1 minus negative 1 over 2. That's 2 over 2, which is 1, right? The amplitude of this function is 1. And I should remind you that the period of a function is the horizontal length of one cycle. That's how we got 2 pi. And amplitude, I said it's the distance from the midline to the max or min. Another way of saying that would be it's half the distance between the max and min values. So if we want to figure out half the distance between max and min, we can do max minus min and divide it by 2. Okay, let's do tan. In order to graph tan, the easiest way to do it would be to remember that a tan ratio is equal to a sine ratio over a cosine ratio. That's the quotient identity for tan. So notice this function has a function in the denominator. So anytime a denominator is 0, we know a function is undefined. So tan is undefined whenever cosine is 0. And when is cosine 0? If we look back at the graph of cosine, cosine is 0 here at pi over 2, and again here at 3 pi over 2, and it would happen again at 5 pi over 2, 7 pi over 2, and so on. So we're going to see asymptotes for this tan function. So to generate the table of values for tan, since tan is equal to sine over cos, we can just take these completed tables of values for sine and cos and do the quotients over here. So sine of 0 would be equal to sine of 0 divided by cos of 0. So 0 divided by 1, that's 0. And then tan of pi over 6, well, we can take the ratio from sine of pi over 6 and divide it by cos of pi over 6. So 1 over 2 divided by root 3 over 2, that's 1 over root 3, which is about 0.58. And then tan of pi over 3, divide these, root 3 over 2 divided by 1 over 2. That gives us root 3 over 1, which is just root 3, which is about 1.73. And then pi over 2, 1 divided by 0. 1 divided by 0 is undefined. So we're going to have a vertical asymptote at pi over 2 for the graph of tan. 2 pi over 3. So root 3 over 2 divided by negative 1 over 2. We get negative root 3, which is negative 1.73. And I think you get the pattern now, so I'll just fill out the rest quickly just by dividing each of the sine and cos ratios by each other. So that's the completed value of tan ratios. So if we plot each of these points, right, the point 0, 0, the point pi over 6, 0.58, and so on, we'll get the graph of tan. So I'm going to start by graphing the asymptotes at pi over 2 and at 3 pi over 2. And then I'm actually just going to graph the things in between those. So I'm going to look just at this section here, the section between the asymptotes, and that's going to give me one full cycle. The period of tan is actually pi, not 2 pi. So let's take a look. Let's plot those asymptotes. And now I'm going to plot the points between the asymptotes. So at 2 pi over 3, the tan ratio is negative 1.73. So 2 pi over 3, negative 1.73. You know, that's approximately right here. And then at 5 pi over 6, the tan ratio was negative 0.58. So negative 0.58, that's approximately here. And then at pi, it was 0. At 7 pi over 6, it was at 0.58. And then at 4 pi over 3, it was back to positive 1.73, which is about right there. So the tan function looks something like this between the asymptotes. It does a little curve through there and up like that, approaching the asymptote. So there's one cycle of the tan function. So now we just have to basically copy and paste that cycle infinitely throughout the domain. So I can start by doing more asymptotes, and notice the distance between these asymptotes, the distance between pi over 2 and 3 pi over 2 is 2 pi over 2 pi. So there's going to be a vertical asymptote every pi units. So I can do some more asymptotes. And I can do 2 more cycles of this function that'll look exactly like that first cycle. And there's another cycle. And there would be pieces of other cycles I could fit on the graph here, but I think that's enough for now. So there's the graph of tan. Let's state some properties of this function. So domain, this function exists everywhere except for at these vertical asymptotes. So I would say x can be any number. X can be any real number given x does not equal, well, how do we summarize? It can't be 1 pi over 2, it can't be 3 pi over 2, it couldn't be 5 pi over 2, 7 pi over 2, or so on. So I say it couldn't be pi over 2 plus, well, the difference between all those asymptotes, right, we said was 2 pi over 2. The distance between here and here was 2 pi over 2. So I can't add 2 pi over 2, so plus 2 pi over 2, any amount of k times where k is any integer value. So I could combine these fractions and make it look like pi plus 2k pi over 2. And I would say where k is an element of integers. If you plug in any integer value for k into this equation, right, if we plug in 1 for k, pi plus 2 times 1 is 2. So pi plus 2 pi is 3 pi over 2. We notice that there, at 3 pi over 2, there's an asymptote. How about if I plugged in negative 1 for k? 1 pi minus 2 pi is negative 1 pi over 2. Notice there's an asymptote there. So that summarizes the domain. So now let's do the range for the function. Notice this function goes infinitely high and low. There's no restrictions on the range. So we'd say y can be any real number. The period of this function, so it's not like sine and cos where the period is 2 pi. It only takes pi units to complete a cycle. It repeats every pi units. So the period of the function is pi. How about the amplitude of the function? Well, since there is no max or min value, we can't calculate the amplitude, right? Amplitude is half the distance between max and min, right? The distance from the midline to the max or the midline to the min. Well, there is no max or min, so there is no amplitude. Now let's do the reciprocal trig functions. To graph the reciprocal trig functions, we just have to remember the reciprocal identities, right? Cosecant theta is equal to 1 over sine theta, right? A cosecant ratio is equal to the reciprocal of the sine ratio. A secant ratio is equal to the reciprocal of the cosine ratio, and a cotangent ratio is equal to the reciprocal of the tan ratio. So let's start with cosecant. And what I want you to notice when we graph these, since each of these functions has a denominator, if the denominator is 0, that makes the function undefined. So anytime sine is 0, cosecant is going to be undefined. Anytime cosine is 0, secant will be undefined, and so on. So they're going to have vertical asymptotes. You can pause the video and read these here, but one thing I want to point out to you is that reciprocal functions do have vertical asymptotes. That's the most important thing on here. They have vertical asymptotes, right? If for an angle input, if it makes the sine ratio 0, that's going to make the cosecant ratio 1 over 0, which means undefined, which means vertical asymptote. And like for secant, when is secant going to have a vertical asymptote? Well, whenever cosine theta is 0, because then we'll get 1 over 0, and so on. So let's graph cosecant first. And remember, cosecant ratio is equal to 1 over the sine ratio. So we just have to take all of the sine ratios, which we calculated earlier, and do 1 over those. So 1 over 0 is undefined. 1 over a half, well, that just flips it, right? The reciprocal of something flips the fraction, so it becomes 2 over 1, which is just 2. The reciprocal of root 3 over 2 is 2 over root 3. Just flip all the fractions, which is about 1.15. The reciprocal of 1 is just 1, right? 1 over 1 is 1. And then I think you get the pattern here, so I'll just go ahead and do the rest of these quickly. Okay, so there's the table completed. Now let's plot each of these pairs of points, and we'll get a picture of what the function looks like. So I'm going to start by doing the vertical asymptotes, and you'll notice that I have a graph of the sine function just kind of faintly in the background here, because we want to be able to look at the relationship between the graph of sine and cosecant. So I'll start with the asymptotes. So there's going to be an asymptote anytime the sine ratio is 0. So the sine ratio was 0 there, there, here. It was 0 again over here, and over at 2 pi, but I can't see that point there, so I'll leave it. So now let's plot all of the points from the table, and we'll see what this function looks like. So the sine ratio at pi over 6 was a half, so for cosecant, it's the reciprocal of that. It was up at 2. At pi over 3, it was 1.15. And the reciprocal of 1 is 1, so therefore you're going to see that the cosecant and the sine function have the same ratio values at pi over 2. Then back to 1.15, then back to 2. So here's what it looks like between those two vertical asymptotes. And then what did it look like down here? Well, all of these sine ratios are negative, which means cosecants are also going to be negative, right? When you flip something, it doesn't change its sign, right? The sine ratio here was negative a half, so the cosecant ratio is the flip of that, negative 2. Here, negative 1.15. The flip of negative 1 is negative 1. Negative 1.15. Negative 2. So here's what it looks like in that section. And that's what the period of this function is. Now it's going to repeat this over and over again. So it's going to keep flipping back and forth between being positive or negative, but the period of this function is 2 pi. So if we continue the pattern, over here it's going to look like this. And up here it's going to look like this. And there's 2 cycles of the cosecant function. If we do the properties of this function, so domain, this function exists everywhere except for at the vertical asymptotes. So x can be anything, given it's not any of the x values at the vertical asymptote. So it's not going to be at 0, at pi, 2 pi, 3 pi, 4 pi, 5 pi. It's not at any integer value of pi. So what we need to write there, x can be anything, given that it's not equal to k pi. And we have to jot down also to mention that k has to be an integer value, and z is the symbol for integers. The range of this function, well, this function is actually, the range is a little weird. It's only at 1 or above, or at negative 1 or below. It's not between negative 1 and 1. So how we write that, we say range, y can be anything, given that it's either greater than or equal to 1, or less than or equal to negative 1. So there are 2 intervals it could fall between. The period of this function, we said it was 2 pi. The amplitude of this function, since it has no max or min, right, it goes infinitely high, infinitely low. There is no max or min, we can't calculate the amplitude. We would say none. Okay, now let's do the graph of secant. The process is very similar to what it was for cosecant, so I'll go through this quickly, right? Secant ratio is equal to the reciprocal of the cosine ratio, so we just have to flip all of these cosine ratios. So I'll do that quickly. Just flip all of these values, right? Do 1 over all of them. So 1 over 1 is 1. Flip this one, becomes 2 over root 3, which is 1.15. Flip this one, we get 2. Flip this one, 1 over 0 is undefined. And I'll fill out the rest quickly. So these are all the ratios for secant. We can plot all of those. I'll start by doing the asymptotes. And remember, the asymptotes are going to be at all of the places where the cosine ratio is 0, because that would make secant 1 over 0. So I'll do those quickly. Okay, now I'll plot the points. So I would start off by getting half of the first section of the function. So 1, 1.15, 2. And I know the other half, it's symmetrical in this little section here. So I know this is going to be at 1.15 and 2. So here's this little piece of it. And then the reciprocal of negative a half is negative 2, negative 1.15. Reciprocal of negative 1 is negative 1, negative 1.15. Reciprocal of negative a half is negative 2. There's that piece. And then I get half of these pieces as well. So here we go. There's that half. And it does continue over there. I get another full piece here. And a half of another piece here. So there's the secant function. So notice the period of this function is 2 pi again, right? If you picture from here to here between those, that's just going to get copy and pasted over and over and over again. It's just going to repeat. Secant is also a periodic function. Let's write down the properties of this one. So this function, the domain, once again, x can be anything, except there are some x values it can't be because there are vertical asymptotes. There's vertical asymptotes at 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Notice it's at all of the places where cosine is 0. So it's going to have the same restrictions as tan, because tan is sine over cos. It also had cosine in the denominator. So the restriction on this, it can't be 1 pi over 2, 3 pi over 2, 5 pi over 2, or so on. So it can't be pi or any multiple of 2k pi over 2, where k has to be an integer value. So I can't add 2 pi to pi any amount of times over 2, because then that would tell me where a vertical asymptote is. The range, it's the same as the cosecant range. So y can be anything, but it has to be either less than or equal to negative 1 or greater than or equal to 1. Amplitude, none, because there is no max or min value. Period of the function, how long does it take to do one full cycle? It was 2 pi radians. So the last example of this lesson is graphing cotangent. So if we want to graph cotangent, we just have to do the reciprocal of all the tangent values. So the process is very similar to how we did secant and cosecant. So I want you to actually try this one on your own. So I'll just pause the video here, try and fill out all of these values, and then try and do the graph of cotangent. And then after you're done doing it, unpause the video and I'll show you the solution. So here's what you should have gotten. So here are all of the cotangent ratios. So have a look at yours, make sure they match. And then look at the blue function, make sure the graph of your cotangent matches the blue function here. Make sure you have the asymptotes in the right spot, right? Anytime the red function tan was 0, we know cotangent is undefined because it would become 1 over 0. So therefore there are vertical asymptotes there. And what are the properties of this function? Domain, x can't be any multiple of pi, right? It can't be 1 pi, 2 pi, 3 pi, 4 pi, so on. So therefore we say x can't be k pi, where k is any integer. The range, it goes infinitely high and low. Y can be any real number. And the period is pi, just like tan, right? One cycle looks like this, and then that just repeats over and over again. Amplitude, none, because there is no max or min. All right, make sure you try out the practice questions now. So on jensenmath.ca, make sure you go here, try the worksheet, and then also there are worksheet solutions if you want to check your answers. All right, that's it.